Hi everyone, myself Jayasree and I belong to a Department of Electrical and Electronics Engineering of Rajagiri School of Engineering and Technology. This is my next lecture on the topic single phase induction motor for EE216 S4A Applied Electronics and Instrumentation. And today the main topics I will be covering are: first one, the conceptual details of plain single phase induction motor, followed by why plain single phase induction motors are not inherently self-starting, and the theory behind it, double field revolving theory. Now, since you already studied three-phase induction motor, three-phase induction motors are extensively used in industries. What's the main advantage? It is inherently self-starting and rugged in construction. Now coming to single phase induction motor, it is extensively used in domestic, industrial and commercial applications where single phase supply is available. We can use three phase induction motors only where three phase supply is available. So wherever you are having single phase supply, you have to go for single phase induction motor. And three phase induction motors are extensively used in industry. It is called the workhorse of modern industry. Now coming to the applications of single phase induction motor, some of the domestic applications: fans, blowers, washing machine, food mixers, compressors. Industrial applications like pumps, conveyors, power tools like drills, presses, etc. And commercial applications like office machinery, dairy machinery, woodworking machinery, small farming machinery, etc. And it is available or designed for fractional HP rating. HP stands for horsepower. And what's the relationship between HP and watts? 1 HP is equal to 735.5 watts. So, the main disadvantage of single phase induction motor when compared to three phase induction motor is that it is not inherently self-starting. We need auxiliary circuits or devices to make it self-start. That topic I will be taking in the next lecture. It will be operating with a power factor, very low power factor. Single phase induction motor generally operates with a power factor of 0.0 PF lag and low efficiency of the order of 75 to 80%, and it is low starting torque. Generally the reason is that we are having cage rotor rather than slip ring, and now for a given frame size and temperature rise, output is around 50% as compared to three phase induction motors. Now the conceptual details: similar to any rotating machine, you are having a stationary part called the stator. Here it accommodates a single phase distributed winding rather than a three phase distributed winding, which is in the case of three phase induction motor. And this single phase distributed winding is wound for a particular number of poles depending upon the requirement for speed, and the rotor standard squirrel cage rotor, and between the stator and the rotor you are having an air gap, and the air gap has to be kept as minimum as possible, 0.5 mm to 1 mm. Otherwise the magnetizing current will be pretty large and the machine will be operating with low power factor, lagging power factor. Now you can see the cut view. Similar to your three phase induction motor, it has got a frame. The frame accommodates a stator core, inside of which is slotted to accommodate a single phase distributed winding, which produces a working flux. Here also you will find that in the subsequent lectures you will find that it is a rotating magnetic field, and you can see the shaft, the rotor, which has got a core. Slots are cut in the outer periphery to accommodate rotor bars, short circuited with end rings, and at the two ends you can see the bearings, generally ball bearing, and an additional thing is present in the rotor, and that is a centrifugal switch, which we will be studying in the next topic. And you can see the terminal box over here. This is the foot. It has got two ends, non-driving end and the driven end. So you can see the drive pulley, rotor, stator, centrifugal switch, bearings, terminal box, power supply, and definitely you are having the cooling fan. To take away the heat to the external medium, you are having a cooling fan. Now we will see why plain single phase induction motors are not self-starting. I am stressing the term plain we are going to study why plain single phase induction motors are not inherently self-starting. The figure 1 shows the cut view. The stator accommodates a single phase distributed winding. The rotor, the standard squirrel cage, and between the stator and rotor you are having the air gap. A plain single phase induction motor with a distributed winding and cage is shown. When a single phase supply is given to the stator winding, the flux will be of alternating nature, and the alternating flux varies sinusoidally in space. Axis of this field is stationary in the horizontal direction as shown in figure 2. So you can see the diagram, stationary flux acting in the horizontal direction. This alternating flux passes through the air gap, cuts the rotor conductors, stationary rotor conductors, and EMF will be induced as per Faraday's laws of electromagnetic induction. Since the rotor conductors are short circuited with the help of end rings, current will flow through the rotor conductors. Direction of induced current can be determined by applying the Lenz's law, and it is shown in figure 2. You can see the direction of current in the rotor conductors by applying the Lenz's law. Now for the direction of the stator field shown, the force experienced by the upper conductors will be in the downward direction, and the force experienced by the lower conductors will be acting in the upward direction. You can apply the Fleming's left hand rule. These two forces are equal, and what will happen? They cancel each other, and the rotor experiences no torque. Thus we can say that plain single phase induction motors are not self-starting. Since it is not inherently self-starting, it cannot be used for any applications. However, if a plain single phase induction motor is given a sufficient push in one direction, it continues to pick up speed in that direction. How the rotor develops torque when it is given a push can be explained with two theories. The two theories are double field revolving theory and the cross field theory, but double field revolving theory is more commonly discussed. Now let us discuss the double field revolving theory. It was proposed by Italian physicist and electrical engineer Sir Galileo Ferraris. So it is known as Faradays Principle. DFRT stands for double field revolving theory. It is based on Faradays Principle. What does it state? An alternating flux can be represented by two phases, each of half the magnitude and rotating in opposite direction with the same synchronous speed. And you already know any sinusoidal quantity can be represented by a phasor, and that single phasor is having a maximum value of phi m. Now this is resolved into two components. A rotating in the counterclockwise direction of magnitude phi m divided by 2, and the next component B rotating in the clockwise direction of magnitude phi m divided by 2. Now the component fluxes revolves in counterclockwise and clockwise direction. After some time, we can see that A and B would have rotated by plus theta and minus theta. At any instant, you can find the resultant. So how can you find the resultant at this point of time? Resultant flux can be determined. What you have studied, this equation you have studied in your engineering mechanics. So twice phi m divided by 2 cos 2 theta divided by 2, and on simplification you will get it as phi m cos theta. Now let us assume that A has rotated by 90 degree in the counterclockwise direction, B has rotated by 90 degree in the clockwise direction. Now at this instant you can see that A and B of equal magnitude are in opposite direction. So what is your resultant flux? The resultant flux is equal to 0. Now let us assume that A has rotated by 180 degree in the counterclockwise direction, B has rotated by 180 degree in the clockwise direction. Definitely this is a resultant, but this resultant will be of minus phi m. Now again continuing the rotation, A has reached 270 degree. By rotating 270 degree, it has reached to this position, and B has reached this position when it is rotating in the clockwise direction. Again, you can see that these two are equal in magnitude but in opposite direction. So what happened? The resultant flux is 0. Now, and after it has completed 360 degree, you can find it at the maximum value, the resultant value is again phi m. So, if the values of the resultant flux are plotted against theta, the angular position, between the limit 0 to 360, that means one complete rotation it has completed, then what you get is not a sine wave but a cosine wave as indicated in figure F. Now, since we are assuming two fluxes, one in the counterclockwise direction and second in the clockwise direction, let SF represents slip acting is the slip produced by the forward flux, and let SB represents the slip for the backward flux. So SF is the slip of the rotor with respect to forward rotating flux, which is B, and SB slip of the rotor with respect to backward rotating flux represented by A. SF, it is rotating with a synchronous speed ns. So SF is equal to ns minus n divided by ns, which is equal to your slip S. Now SB, slip of the rotor with respect to backward flux, SB is equal to minus ns, since it is rotating in the backward direction. So it is minus ns minus n divided by minus ns, which is equal to 1 plus n divided by ns. On further simplification, you will be getting it as 2 minus s. So two expressions, slip of the rotor with respect to forward field, SF is same as F, and slip of the rotor with respect to backward field can be written as SB is equal to 2 minus S. Forward and the backward flux, while revolving round the stator, cuts the rotor conductors and produces a torque, one which can be called as a forward torque acting in the clockwise direction, and the second one a torque acting in the backward direction which acts in the counterclockwise direction. And you are having a resultant torque TR is equal to TF plus TB, both in magnitude and direction. Thus, we will see the torque slip characteristics according to double field revolving theory. We will see that at every slip the rod is subjected to two torque. You can see the characteristics. Actually, in this torque slip curve, three curves are drawn, one related to the forward one and the second one related to the backward one, and at any slip you are having the resultant torque slip curve, and you can see the dashed one is the resultant one. This is pertaining to backward, and this one is pertaining to a forward, and this one is corresponding to the backward. Now at start, at start the rotor is a standstill condition, S is equal to 1. The forward field as well as the backward field develop the same torque. You can see corresponding to the forward one, and this is corresponding to the backward one. Both are equal in magnitude but in the opposite direction. Hence you can find that, you can see that TR is passing through 0. Thus we can say that plain single phase induction motors are not self-starting. At any other slip, the torque slip curve has been plotted between 0 to 2. Now any other slip other than 1, you can find that there is resultant torque. So that every other slip, the rotor is subjected to 2 torque given by TR is equal to TF plus TB. Now, if the rotor is given a sufficient push by some means in one direction, slip not equal to 1, and we had seen in torque slip curve, we had seen that there is a resultant torque. If this torque is more than the load torque and the frictional torque combined together, then the motor can pick up speed in that direction. So we have seen that plain single phase induction motors are not self-starting, but a motor should be designed in such a way that it is self-starting. A not self-starting machine is of seldom no use. So a motor should be designed in such a way that it is self-starting. Several methods are developed to make it self-start. The stator winding is generally modified or split into two, split phase type, each displaced in phase to make it self-start. Different arrangements are there to make it self-start, which we will be studying in the next lecture. So, thank you. Now, the reference books, you can refer these 3 books, AC and DC Machines, Volume 3 by B.L. Thereja and A.K. Thereja, Induction Synchronous Machines by Murikesh Kumar, and The Theory and Performance of Electrical Machines by J.B. Gupta. Thank you once again. Thank you.